So yes, welcome back. Wanted to point out on the syllabus, as announced and as reminded over email, link to the homework portal now available. Homework 0, worth 2 points extra credit over the syllabus, should take you a good 5 minutes. Have you tried it yet? Couple people? Any questions? Any problems? No results section this semester, yes, for this class. It's all multiple choice because the written examples, like the ones that I present in class, have a big, long results section, and you can use those as templates instead. There's not as much of an algorithmic way of writing results sections for measurement models. It's not as easy. So there's no results sections of the drop-down kind that you're used to. So for better or worse. Know how you feel about that. But if you can please, folks, if you haven't done so already, give it a shot. Hopefully by next week. That way, if there's any problems with the logins, I can get all of that sorted out before the real homeworks are starting to be due. So I will let you know next time something is available for you to work on. All right, so that's that. We got this. Shall we talk about classical test theory? And by we, I mean I talk and you ask questions. Seem fair? All right, that's a good deal. So, classical test theory, away we go. So what are we trying to do? Always good to keep the big picture in mind when we get into the weeds here. We're measuring latent traits. Latent meaning something we can't observe directly, so we have to collect some kind of information that we believe to be influenced by the trait. And the trait in this case has many, many synonyms. Today it's going to be called true score, capital T. Later on it will be called factor score, latent variable, latent construct, latent trait, latent, all the stuff. And then theta eventually. And as a reminder, we are always in this course going to assume the trait is continuous. So if you're interested in measuring something latent that is a kind or a category, there are different models for that I can point you towards. How we do it is to collect observed responses. You're going to hear the word item or indicator from me interchangeably, but if you have other types of responses, like trials can be considered items in some contexts, whatever it is that you're referring to as outcomes that the trait is predicting. That's what I mean by indicator. And these can be any kind. So indicators don't have to be quantitative variables. They can be binary, they can be ordinal, they can be nominal, they can be counts, they can be anything that you need. How do we know if we've done a good job? We collect evidence using the responses. And we are going to build a composite for now, but then starting in the next unit, we were going to do item level measurement models in which the latent trait is the predictor and the outcomes are the responses. So big picture, the things that people care about when they are building a new instrument or asking questions about an existing instrument and how well it functions, basically validity and reliability are the two main things. This is about the extent of what I'm going to say about validity in this course. I used to wave my hands at it more, but that got pushed out in terms of other stuff. So the extent to which it measures what it is supposed to. You know, we have these traits, we have an idea as to what they should be, but we have to provide some kind of evidence that we're right, like the name that we've created for our trait is the right name. That is usually answered by some kind of external evidence. So once you get a latent trait measurement model built and you have individual differences in this trait, what are they related to? What other things does it predict? What other things does it not predict? Does it correlate in expected directions? All of those sorts of questions are external. Like they get answered in a separate set of analyses with different kinds of data pulled from external sources. So I decided not to spend a lot of time on that because we're focusing on just the items and the traits in this class. But a precursor to validity and being able to look at those sorts of analyses and questions is reliability, the extent to which the trait is measured with sufficient consistency. And there's a quote that I like, and I can't remember where I got it from, but it's not mine. Validity is measuring the right thing. Reliability is measuring the thing right. Reliability indices are going to vary across this course. Like today, we're going to talk about alpha and Spearman-Brown reliability. In the confirmatory factor models, it's going to become omega and factor score reliability. And in the item response theory unit, it's going to be called test information. But the same concept in terms of how consistent are the responses to the how consistent are the traits being measured is the question. So all of this is predicated on knowing ahead of time that you have dimensionality right, because reliability is for one thing. And if you make an assumption that all of your items are measuring the same one thing and you're wrong, then whatever reliability coefficient you get out of that means nothing. So all of this in this lecture, until we get to the point where we're fitting measurement models predicting item responses, we're assuming we know the dimensionality. We're just assuming it's one thing, and therefore we can do all this stuff based on the idea of a total score. What we can do, add stuff up. So classical test theory, the big picture of it is this little equation right here. The idea that your total score that you get by summing or averaging the responses to your indicators is a function of your true standing on a trait, so true is a person thing, and then error. Why is it that your score is off from what it should be? We don't know. So the true score is thought to be the best estimate of the latent trait in these models. It is not separable from the latent trait itself. And there are things that we can do if we make certain assumptions to be able to figure out how much of the total variance in this true score, or in this total score, excuse me, is due to true versus error. And that's reliability. To do that, though, we need a little bit of basic math. So this is just to remind you that you've seen this stuff before and you're going to see it again. We're going to need to know how to make a mean, need to know how to make a variance. Covariance, which is something that doesn't show up a lot in other classes, but it does here, is relationship in an unstandardized original metric. So covariance is difficult to interpret in terms of a number because it's tied to the scale of the things that are covariant. If it's positive, you know that as one answer goes up, the other one is likely to go up. And if it's negative, as one goes up, the other goes down. But like your covariance could be 3 or it could be 300, and you don't have a sense as to whether that's a lot. For that reason, we often look at correlations instead, in which the covariances are standardized using the standard deviations of these two things. So this semester, we're going to talk about covariance matrices a lot, a whole lot. And so variance-covariance matrix is a phrase that you'll see. I will shortcut that to covariance matrix a lot of the time, where the diagonal has the variances of the item responses, and the off-diagonals have the covariances. In a correlation matrix instead, the diagonal has ones, because that's what a standard deviation is in standardized land, and the correlations are on the off-diagonals. So, what about categorical indicators? Can you do any of this on categorical indicators? It gets a little tricky. So when the numbers are actually numbers, all of those things are straightforward and believable. But most of the time in social science measurement, maybe not necessarily educational measurement, but in other areas, we're collecting responses using categorical response formats, binary, ordinal, or nominal. And I have the synonyms here that people say for this. Dichotomous just means 2. Binary specifically means 0 and 1. I tend to think of those interchangeably, but just to make that point. This word right here is always said wrong when I need to say it, but it's somebody's name. It's not a Likert scale, it's a Likert scale. There, I think I got it right. It's like one of those things that it always leaves my brain in the moment I need to say it correctly. Multinomial is a synonym for nominal, but I think it's a bad one because it actually refers to a distribution and not a type of measurement. But if you see those terms, then. So if we have a binary indicator, 0 and 1, we can still find means, we could still find variances, and we could still find covariances. We could do the same if it's ordinal, but not if it's nominal. However, in the case of binary, there's something important to keep in mind, that the extent of relationship across binary items is going to be limited if we compute means, variances, and covariances in the usual way. So for something that's binary, the mean of a 0-1 variable is usually labeled as P for the proportion of values of a 1, and Q is the opposite, the proportion of zeros. So the mean of a binary variable is just the proportion of 1s. The variance is the proportion of 1s times the proportion of zeros. And so that means that a binary variable has a maximum variance if it's half and half, 50% 1s, 50% zeros. And as you move the mean away from that on either side, the variance diminishes to the point where at the ends it's just a constant. So this type of shrinking variance is going to cause shrinking covariance with it. And what will happen is that if you ask for a correlation matrix, for instance, across binary variables, they don't have a maximum correlation of 1. They don't. The only situation in which that's true is if both variables have a mean of 0.5. So binary data is going to shoot you in the foot if you use traditional measures of association and then by extension reliability. So that's foreshadowing. For ordinal indicators, if I have something like this, 1 to 5 levels of agreement, I could make a mean, I could make a variance, but these aren't really numbers, they're ordinal. So this scaling system is equally ordinal. The distances are not assumed to be equal. And we have the similar type of range restriction issue at play here. The maximum variance that an item can show depends on how many categories it has. So to the extent that variance is limited, covariance and association is limited, and reliability is going to be limited. There's ways around that, and you will see them. So, terminology time. 2 words that you're going to hear throughout the semester: item difficulty and item discrimination. Indicator and item are synonyms in this context, but when people talk about it, it's always the word item. These are considered properties of an item. How we indicate those properties, how we index them, depends on what kind of model framework we're working with. Classical test theory does one way. Latent trait measurement models literally estimate item parameters for these things. So difficulty is the idea of location. Like along your latent trait, remember the construct maps, ordering items and people? Where is your item? Who is it for is the way that I think about this. Like what kind of trait level is likely to get this item right, or to say, yes, I endorse this, or yes, this has happened to me. You can think of it as severity if you're interested in a trait that's not ability-centered. So how bad is your case of whatever this condition is? And if you're that bad, how likely are you to say that, yes, this is a symptom of mine, or no, it's not? So to measure people with a range of trait levels, we want to have items everywhere. And to the extent that you have holes in your trait, right? If you have a whole bunch of really hard items, you're going to have a good measure of people that are high on the trait, but not so good on people that are low on the trait. So this is something that we pay attention to make sure that we can measure people of various levels of ability. Discrimination, on the other hand, is how good the item is at differentiating people of different traits. So it's how discriminate. You'll hear that word. This should always be stronger is better. So you want the item to have as strong of a relationship to the trait as possible, but this gets limited by its location in some cases. So in classical test theory, the way that these 2 ideas are operationalized, because our best guess as to what someone's latent trait is the total score. Total score does the heavy lifting. So the indicator's mean is considered the index of difficulty or severity. So the proportion of people who got something right, or the mean on the ordinal item that you're pretending are actually numbers, that's your indicator of difficulty or severity. However, it's backwards. If 90% of my class gets an item right, is that item difficult? No, it's easy, right? But that's high difficulty in the way that people talk about this. It's backwards. Why? I don't know. I didn't make it up. I didn't. I'm just the messenger here. I think it's confusing. I think it's okay because it's confusing to talk about item means as indicating easiness instead. Anytime you have things that are additive rather than subtractive, is that a word? Subtractive? Okay, it is now. If additive is a word, I think subtractive is a word. If you have something that's additive, then I think it's easiness is the right way to talk about it. If it's subtractive, like in IRT models, then it really is difficulty and it's backwards. Side note on this, for the same reasons, when you're thinking about what to name your latent traits, make it go the right way. For example, on my weather app on my phone, I'm holding up my hand like my phone's in it. Just pretend it is. It's on Do Not Disturb though. On the weather app, there's various sections for temperature, precipitation, wind, and one of the later ones is called air quality. You have this before? It's like rainbow. What does a high number on that mean? Bad air quality. So that is not an index of air quality. They need to change the name. It's like particulate matter or badness of air. So think about that when you're describing things, like if you have a scale where everything's being reverse coded, everything is, that you're not measuring the thing you think you are, you're measuring the opposite. So naming things so that more means more of the trait in a way that's readily interpretable will help your readers and other stakeholders stay with you. But I can't do anything about this. This is what it's called. This is generally not considered in classical test theory because it doesn't really contribute to anything. However, it can relate to problems of discrimination. If you have an item that 95% of your people got right, that item has very little variance. It has little potential to show covariance and association. So it can look like a bad item having low discrimination because it's functionally a constant. I would argue you still need to keep it if you want to measure that level of extremity in terms of someone's ability. An item where 95% of the people got it right is going to be very useful at discriminating across lower ability people. So if you want to do that, then you might want to keep it even if discrimination is on the low side. Discrimination in these models is indicated by something called an item total correlation, or item remainder is how it's usually done in practice. It is the correlation of the item, a Pearson correlation specifically, with the total score. And so that the total score doesn't contain the item, that's why we get into item remainder. So item remainder or item rest is what it will look like in your software. It's the correlation of the item with all the other items except that one total. Does that make sense? So it's not inflated by correlating something with itself. So this is only possible to do because they're using Pearson correlation for binary or quantitative. And ordinal is if you pretend that they're numbers, which a lot of people do, especially in this context. Once we get into measurement models, then discrimination is a slope. It is the slope that multiplies the latent trait in predicting the outcome. So it's going to be different, but it's the same idea as a concept. Stronger is better at discriminating across people. So Pearson correlation is the key thing here that makes this problematic for binary items in particular. Reliability then, we are treating the total score as a quantitative variable, even though it technically is ordinal because it's a combination of ordinal things. The goal is to measure reliability as consistency. So the examples that we use from like the physical sciences, like if I have a bathroom scale and I step on my scale, I get one number. If it's a good scale, if I hop back off and hop back on, it should be the same number, right? Ideally, if I weighed myself 100 times in a row, I would get the same number back with very little variability. And that's how we think of as reliability. Now, is my weight correct? Just because I got the same number 100 times does not imply that my weight is correct. That's validity. That's a different thing. So to figure out if my weight is correct, I need to go to someone else's scale and get converging evidence as to how far off my answers are from something else. Right? So validity is sort of a separate line of argument. So like that's the way we think of reliability, as consistency. Like if I were to do this over and over again, the true score is the mean across these infinite replications. But in practice, we don't collect that kind of data. When we do psychometric evaluation, how many times do we get people to answer the questions? Once, usually, right? And we're like, well, then let's just get a lot of people. Can we make that work? We'll get a lot of people, and then they'll do it once, and then we'll use these formulas and we'll get reliability. Conceptually, like that doesn't work. We're substituting between subject variance for what is a within subject kind of process. So there's a theoretical disconnect that I don't like and I want you to be aware of with respect to that. All right. Equations are next. That makes it a good time to say, how are we doing? Thumbs? Zoomers? Cats? The cat's tail is up. Can I interpret that as a thumb up? Yeah, the cat likes the lecture. So some sideways still. Yeah, okay.
Last class it was here. Now we're kind of.
Oh, man.
It's okay.
It's okay. Yeah, that's all right. See, I don't expect reliability of your thumbs because it could actually change based on what's happening, right? That's a signal there. That's not noise. How can I make it go back?
I think it just needs to sink in.
Fair.
You know, like
Yep.
I don't think there's anything that needs to be done.
Okay. I just thought I'd ask. You have ideas. Anyone else have comments, questions, reactions? No? All right, moving on then. So reliability in classical test theory is often indexed by the correlation between two scores of some kind. Here is the math by which that becomes believable and the assumptions that you have to make for that to work. So first off, each of these is a different set of items somehow. We'll talk about the various ways that can happen next. The same true score and two different errors to go with the two different values here for the total score. So we have to assume that the errors have equal variability. Okay, that's not too bad. That the total scores have equal variability. I'm not so sure about that. That it's the same trait or true score both times. Okay, I'll give you that one. That the errors are uncorrelated with each other and with the true score. That could work. The reason we can say the errors are uncorrelated is that the only reason why these y's would have been related is supposed to be t, and what's left over is uncorrelated. That is a testable assumption if you actually fit a model. So then if you believe all of these things and you try to compute a Pearson correlation between these two total scores, you have the covariance between them first in the numerator here, and the standard deviation of each in the denominator. That's the formula for Pearson correlation. Well, now let's unpack it. Y1 is actually this stuff right here. Y2 is this stuff right here. So we write it out that way next to try and illustrate the idea that these are things packed into total score that we want to differentiate. We still have the bottom denominator the same. Then the next step is something I thought I'd never see again after 8th grade, FOIL. Right? First, outer, inner, last. Nailed it. So then we FOIL. We put the T's together, the T with the E1, the T with the E2, and the E's. But guess what, folks? All these assumptions mean all this stuff cancels out. Further, the bottom, if these two standard deviations are the same, then we don't need to worry about that either, and here we go. So then it just boils down to reliability is indexed by the correlation between these two things, if we believe all these assumptions. So here are the ways we would get two things. Test, retest, two different forms, cut a form in half, or what is done most commonly in practice, alpha as an index of internal consistency. And I have a link here to a paper that introduces the term ergodicity as this idea of the dissonance between assuming that we can get one answer from a whole bunch of people, and that variance is a good way of representing what we would have gotten with one person and a whole bunch of answers. Within person versus between person associations. So there's a link to that if you're interested in more on that. So test, retest reliability is something that folks do when they're trying to validate a scale. By the way, never say that. Don't ever say your scale is valid or it's been validated. That's a red flag because your evidence towards validity is never done, right? It's not like a cake where it's out of the oven and you don't have to worry about it anymore. So evidence for validity or evidence for reliability is a much better way to put it. But when people do research studies on an instrument so that they can validate it, one of the things that is very common to do is test, retest reliability. You give your measure, you wait some time, you make them do it again, and the correlation between the measures is supposed to indicate consistency. Well, what could go wrong? Oh, I don't know, development? Everything?
Literally.
Yeah, like everything. Change? You know, like pre-test, post-test designs are to measure change. But tell me what the difference is between a test, retest design and a pre-test, post-test.
Wait, can you say that question again?
Tell me what the difference is between a pre-test, post-test design and a test, retest design. Whether something happened in the middle. Yeah.
There's change and one doesn't.
Yeah, so for the control group, it's test, retest. For the treatment group, it's pre-test, post-test. That's the best I can do. But even if you don't do anything deliberately, are you the same person that you were 3 months ago or 3 weeks ago or whenever this happened? Not if you're in school, right? Like that's the point of school, is to change. So this could be a person thing. And by the way, if you're interested in measuring reliability of change over time, pre-test, post-test is the worst thing you can do. Let me put it to you this way. If you were going to take a test that determined whether or not you get to have your career, like the bar exam or a nursing exam, do you want 2 items on that test or do you want 200? 200 would give you a better chance at like showing your knowledge, right? And hopefully passing the test. So let me ask it this way. If I want to measure change, do we want 2 occasions or 200? Same principle. So the extent to which someone is high on a trait at one time and the extent to which they change on that trait across time, those are 2 different traits. And to the extent that the latter creeps in there, you can have a lower correlation. People sort of resort themselves because of differential change. Also memory. If you give someone the same test over and over again, they will remember things. So then that creeps in there. If they remember how they answered last time, that changes the situation. And this could work either way. So if you remember what you said, then your scores could go up. If you hate this and you don't want to do it again, your scores can go down. So the 200 items is only good if you can complete them in enough time for these problems not to set in. Also, how long do you wait? Long enough that you don't change, but short enough that you override the memory problem? There's no easy answer for that. So then they're like, all right, let's not do that. Let's get 2 versions of the test. Let's make an alternate form. Like the PPVT has 8,000 alternate forms, right? There was RM and there's 3A and 3B and then there was 4 and I think there's 5 now. Is that up to 6? No, not yet? Okay, I did a paper about this actually, looking at this. And spoiler alert, folks, 3A and 3B are not equivalent forms. If you go down to like the item chunk level, I forget what those are called. Do you know what I'm talking about? Like there's like sections.
I know what you're talking about, but I don't.
Anyone? Item chunk? Can come up with the right words for this?
It's like the section.
Yeah. So they're not parallel, but that's what another option is to take your items, divide them into 2 different forms, and then give each person both forms. Well, that only works if you're willing to believe that they're parallel and that the means, variances, and covariances among the items would all be the same across the 2. And then it's like, well, what if I don't have another form? Can I hack split half reliability into alternate forms? Sure you can. Let's take my test and cut it up. Put it in half. Now I can make my correlation. Now I get my index of reliability. However, it's based on half as many items. That seems like a problem. So then comes into play, no, what if? What if we could extrapolate how reliability would improve if we just wrote more items? And there's a formula that you will see in classical test theory books on this called Spearman-Brown prophecy formula. I like that one, prophecy, right? It's not just a theory, it's a prophecy. And it looks like this. New reliability is 2 times the old reliability divided by 1 plus the old reliability. So for instance, if I had fewer items, I could figure this out. And my reliability by having more would be 0.86. So this would be 2 because I have cut my stuff in half. This formula, by the way, do you see anything in here that pays any attention to your items and their properties? Nope. Whenever you see that, that means you're assuming parallel indicators. All items are equally good at measuring the trait. All items have the same amount of error variance. Those are testable assumptions, and I will show you how to do so. So my problem with a lot of this stuff, because you can probably tell from my voice I have a little bit of snark creeping in today, just like, this much, is because there's all these assumptions that you have to make to be able to use these formulas, and we have ways of testing them. So doing this stuff first before you know that your assumptions are met, to me, doesn't make a lot of sense. That's the basis of the snark. So what can go wrong? Things aren't parallel. That's in a nutshell. Another one is split half reliability. If you cut your scale in half to make 2 forms, how do you do it? And I work with some folks from psycholinguistics that are working at the University of Kansas, And they were interested in looking at measurement properties of a new measure of English vocabulary that they made. And they sent me some articles were all about different ways of doing split half reliability. You know what I'm talking about?
Yeah.
It's like a whole thing, like there's an R package that will make all the possible combinations for you so that you're not just picking one. Because if you do like even odd items, that could have problems. And if you do the first items and then the second set of items, that could have problems. It turns out, though, this problem got solved like in 1950 because that's what alpha is. So what people call Cronbach's alpha, note there's no H in here. It took me a long time to not put the H in. And what Gutman-Cronbach alpha is sometimes called, such as by Rod McDonald in his textbook, because that guy got there first, that is the mean of all possible split half correlations. So this idea of two forms, and I correlate the scores, and that's my reliability, like this is the logic by which we get to alpha, is because it's the mean of all possible split half correlations. Internal consistency is a term that I see a lot of people use still. I don't really have much to say about whether that means anything because alpha doesn't mean anything. Here are the assumptions that you have to make to believe alpha as a measure of reliability. Unidimensionality is the biggest one. Alpha is per trait. So if you are lumping items together that measure different things, alpha doesn't make any sense. Like a total score from multiple subsets. And here's some new vocabulary words. Tau equivalent, or true score equivalent, meaning equally discriminating. This translates in practice to a covariance matrix where all the covariances are the same. Parallel items translates into a correlation matrix where all the correlations are the same. The difference is that whether you enforce the sameness on the error variances as well. If you do, that's parallel. If you don't, it's this one. And the last one is that there's no unaccounted for multidimensionality. Local independence is what this is sometimes called uncorrelated errors. That the trait is the only reason your responses were correlated, the end. All of